picking up where we left off. Hopefully it works this time. It's my third try at it. Anyway, a regular polyhedron is just a polyhedron where all of your faces are regular and they are all going to be congruent to each other. So that's why you see all the tick marks that are here. All of these triangles are all equilateral triangles, equiangular triangles, and they are all going to be congruent to each other. Now, as far as polyhedrons go, there are actually two types. There are concave polyhedrons, which just means one of those polygons is concave, meaning that face or that side got caved in. Just like our regular polygons, we do not really worry about those concave polyhedrons because they're not going to have any properties to us to help us. Instead, we look at our convex polyhedrons, which just means that there are no concave faces. If you want to pause the video and work on these three examples, they're just like the examples we did prior. If not, you can go ahead and follow along. First question asked wants to know, are they a polyhedron or not? So, when I look, it has to be made up of all polygons. For A, I have the square on the bottom, and then our four triangles that go around. So it is a polyhedron. For number 2, unfortunately, I do not have all polygons. I have my curved face there, so it is a no. In number 3, I have my 2 triangles in the front and the back, joined by my 3 rectangles coming around. So since they're all polygons, it is yes. B wants you to be able to go through and name that polygon. So for number 1, it is a pyramid, and then we just have to identify the base. So the base here is that square on the bottom. So it is considered to be a square pyramid. In number 3, this is a prism, and it's actually one of the harder ones that we work with, because most people want to look at that prism and say, well, there's a rectangle or square on the bottom, so it's a square prism. But remember, your bases of a prism, they are the non-rectangles. So in this case, it is these triangles that are in the front and the back that are parallel to each other that are your bases. So it is a triangular prism. And then for C, it's just a counting game. Wants to know how many faces are there. So when we look at the first one, we have the square on the bottom and then my 4 triangles. So there are 5 faces. For the vertices, I have the 4 that go with my square, and then the 1 that is up top. So there are 5 vertices. For my edges, I have the 4 that go for my square, and then the 4 that are with my triangles connecting that square to the top. So there are 8. In number 3, for your faces, you have the triangles in the front and the back, and then the 3 rectangles that come around. So there are also 5 faces. For your vertices here, I have the 3 that are in the front with my front triangle, the 3 that are in the back with that back triangle. So there are 6. As far as the edges go then, I have the 3 to my triangle in the front, the 3 to my triangle in the back, and then the 3 that connect those 2 triangles together. So there are actually 9. Now, in your note packet, you'll see the idea of platonic solids. Really, all you need to know is what a platonic solid is. They are known as your regular polyhedrons, such as the most familiar one to you is your cube that's here, meaning all those sides are congruent, or all those, I shouldn't use the word side, sorry. All of those faces are congruent to each other, and they are all regular. That's why they're all squares. Right? But these are the 5 most common ones that you see here. Now, a cross-section we'll deal with here in a couple minutes, but essentially what a cross-section is the intersection of a plane and a solid. It's if you were to take some solid and cut a little 2-dimensional piece out of it. And we'll show some examples here in a couple minutes. Right. One of the last ideas here in 12.1 is what is known as Euler's theorem. If you look at all these faces, vertices, edges that we've written down, there's always a pattern. So I'm going to go back up to the last 2 examples we did. Most people, when we go and we actually take a look at the pattern that goes on here, talk about taking those faces and vertices. Faces and vertices, we get 10, and then there are 8 edges. Faces and vertices, we get 11, and there are 9 edges. that little pattern that's there will always be true. The edges is always 2 less than the sum of your faces and vertices. So it's a little quick way to double check that you counted correctly. Now, what Euler's theorem actually says is faces plus vertices equals the edges plus 2. Most people, though, will add your faces and vertices, subtract 2, and then compare it to your edges. As far as your types of solvents, all right, all through chapter 12 here, we are going to deal with all 5 of these types. There are your polyhedrons, meaning they are made up of all polygons, your pyramids and your prisms. And then there are your non-polyhedrons, your cylinder, your cone, your sphere, because they have rounded parts to them. Right? That's why they are non-polyhedrons. So it says, find the number of faces, vertices, and edges of our regular octahedron. And it says, use Euler's theorem, or check your answer using Euler's theorem. So, we got to count. Faces. I have the 4 triangles going around the top, the 4 triangles going around the bottom. I cannot count whatever shape, if this is a square, rectangle, I cannot count it because it's not out on the surface of my polyhedron. So there are only 8 faces here. For your vertices, we have 1, 2, 3, 4, 5, 6. For your edges, I have 1, 2, 3, 4, 5, 6, 7, 8, and then the 4 that come around here, 9, 10, 11, 12. Right? 8 plus 6 is 14. 14 minus 2 gives me 12. Quick way to double check that we counted them correctly. Now, we talked about that idea of a cross-section. A cross-section is that 2-dimensional piece that you would cut out of your 3-dimensional figure. So here, in my triangular pyramid, it is that triangle that we would cut out here, would be our cross-section. And the last 2 things that we're going to look at is just some examples of them. It just says, describe the shape formed, taking that intersection of a plane and the cube. So if I cut it horizontally, I end up with a square, since it was a cube to begin with. If I go diagonally here, now I end up with a rectangle. If I cut it at a slant, so this top part is longer than my bottom part, they're still parallel to each other, so we end up with a trapezoid. Last set of examples then, describe that shape form. If I cut that cube just through the little edge there, I have that little 3-dimensional piece, it's just a triangle. In my cone, that cross-section we cut out, if I come through horizontally, is a circle. And if I come through vertically in my hexagonal prism, I cut out that hexagon that's there. Right, and that's what a cross-section would look like. As far as your homework goes, we're looking at pages 798 to 799, numbers 3 to 6, and then 11 to 27, the odds only. All right, everyone. Hope everyone's staying safe, and hope things are going okay for everyone. This is our last chapter, as we talked about. We'll just see how things go and go from there. All right, everyone. If you have any questions, please email me.